Hello. So today I want to discuss about a problem that appeared in CMI 2019 entrance exam. It's a problem on function-based limits. So the question says I have a function that maps R2 to R such that f of a comma b equal to limit n tends to infinity 1 by n into log e base e power na plus e power n. This is defined for all real numbers in a and b. Then I have to check whether f is onto or not. Whether do we have f of 0 comma x is identically equal to x for all x greater than equal to 0 or not. Whether the map x goes to f of a comma x, whether the map is continuous or differentiable or not. I have to check these things. So let's do this out.
This video is sponsored by Chinta.com. Since 2010, Chinta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
We have f of a comma b equal to limit n tends to infinity 1 by n into log of e base e power na plus e power nb. Now to solve this, let's first assume that without loss of generality, assume that a greater than equal to b. We'll deal a less than b the case later using analogy. In that case, I'll just express in this form log e base e power na plus e power nb. This is same as, just take e power na common. So it is 1 plus e power n into b minus a, but I'll write it as e power minus n into a minus b because a minus b is positive and that would be important. So this is log e to e base e power na, that is na into log e base e, that is 1, plus log e base 1 plus e power minus n times a minus b. Call the sequence to be xn, that xn equal to 1 plus e power minus n into a minus b. So my f of a b is just limit n tends to infinity na by n, so that is a, plus limit n tends to infinity log xn by n. Let's see what about log xn. I have xn to be this thing. Now where does xn go as n tends to infinity? 1 plus e power a minus b whole to the power n, and this is the limit. And okay, write limit beside it. And e power a minus b is a positive constant. As a greater than equal to b, e power a minus b is just a positive constant. So when a equal to b, it will have a problem. So assume a is strictly greater than b. So e power a minus b is strictly a positive constant, and that is not 1 because a is not equal to b. In that case, it taken to the power n whole to the power minus n. This is minus n. So when I take it to the power minus n, this goes to 0. Because as a minus b is strictly greater than 0, e power minus a minus b is strictly a positive number greater than 1. So taken power to the power n, this sequence goes diverges to infinity. So taken power to the power minus n, this goes to 0. So xn goes to 1 as n tends to infinity. Now as the map as the map x goes to log e base s is continuous at 1. It is a continuous map. It looks like this. So for all sequences, xn goes to 1 would imply f of xn should goes to like log xn should goes to log 1. Goes to log 1, and that is 0. So my sequence log xn goes to 0. Then what is my f of a b then? f of ab is a plus limit of 1 by n times log xn. And 1 by n and log xn both sequence individually converges to 0. Both goes to 0. So the product also goes to 0. So what we get that for a greater than b, f of ab equal to a. Similarly, you can just prove that for a less than b, f of ab equal to b. This is our 11 action exercise. Similarly, and for a equal to b, I have f of a comma a equal to limit n tends to infinity 1 by n log of e power na plus e power na, so 2 e power n. And this, what is this quantity? This is 1 by n times log 2 plus log e base e power n, that is just n. So that is just a plus log 2 by n, and if you take n tends to infinity, so this goes to 0. So for a equal to b, so f of a comma a equal to a. So for a less than b, f of ab equal to b. For a greater than b, f of ab equal to a. From that you can easily guess what is f. Your f of ab is just maximum of ab. So for a greater than b, it is a. For a less than b, it is b. And for a and b to be equal, then it is either of ab. Now we can easily tell that f is onto, because pick any real number r. If r is greater than 0, we can just take f of minus r comma r to be maximum of r of minus r, and that is r. Like for r greater than 0, I can take minus r comma r to be its preimage, and if r is less than 0, then 2r is smaller than r if r is less than 0. In that case, f of 2r comma r equal to maximum of 2r comma r, that is also r. So in either cases I get an preimage, and for r equal to 0, I have f of 0 comma 0 equal to 0. So for any positive, negative and equal to 0 real number, I have corresponding preimages. So f is onto. Now what about the map x goes to f of a comma x? Like x goes to maximum of a comma x, whether is it continuous? See, maximum of a comma x, it is just mod of a plus x plus mod of a minus x by 2. This is an easy thing to observe. Like when x greater than a, this will be just a. Sorry, this will be just x. When x less than a, this would be just a. Now this maps that x goes to mod a plus x and x goes to mod a minus x, both are continuous. Both are continuous maps, and sum of continuous and product of continuous maps are also continuous. Like dividing a continuous map by a constant number, that is also continuous. So using this, you can easily tell that this map is also continuous. Is continuous. Okay, how does the map look like? That x goes to maximum of a comma x. Like the function is maximum of a comma x. So say this is my a. So when x is less than equal to a, for that it is just a. And when x is greater than equal to it becomes the line y equal to x. You can see this is a continuous map. But it is not differentiable, because see, it has a sharp turn, like it has a very sharp edge, sharp point, and differentiability is a measure of smoothness. So whenever in a graph you have sharp edges like this, like y equal, for example, like y equal to mod x, like at those sharp points the function may not be differentiable. Like for this function, if the graphs look like this, at this high peak point where the graph is very sharp, at that point function is not differentiable. You can easily see that, because differentiable is a measure of slopes, And when you go from this direction, the slope is negative, and when you go from this direction, the slope is positive. So the corresponding limit of slopes that doesn't exist, so the function is not differentiable. Here you can also guess the same thing, because if you approach from left, the slope is 0 always. But when you approach from right, the slope is 1, because from right the slope is same as the function y equal to x. That means the function x goes to f of x comma b is not differentiable. This map is not differentiable. You can easily prove it using your usual definition also. Limit, call this to be g of x. So g of x equal to maximum of x comma b. I'll show that it is not differentiable at b. So limit, its derivative should be of this limit, that limit h tends to 0, g of b plus h minus gb total by h. And this is what? Limit h tends to 0, maximum of b plus h comma b minus maximum of b comma b, that is b, divided by h. Now you can easily see that you make two cases. When h tends to 0 plus, what does it become? As h tends to 0 plus, b plus h is bigger than b, so it is just b plus h, the maximum of b plus h comma b is subtracted with b and divided by h. So this is by h, this is 1. And when h tends to 0 minus, then b plus h is smaller than b, so in that case this is just maximum should be b. This is b minus b by h, that is 0. So from left your slope is 0 and from right your slope is 1, just like this picture. So from that you can easily see that g is not differentiable at all points. There are some points where it is not differentiable. So if it's not onto, this is false. If it's onto, the function is continuous everywhere, this is true. The function is differentiable everywhere, it is false. The function f of 0 comma x equal to x for all x greater than equal to 0, it is true, because in that case f of 0 comma x equal to maximum of 0 comma x, and as x greater than equal to 0, so it is x. So this ends the solution here and we are done, because we have checked all the cases. Second and fourth options are true, first and third are false. So we are done.
Chinta programs are designed for students who are passionate about mathematics, and they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Chinta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Chinta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit chinta.com.